The forest wakes in slow gradients of light. Shafts of dawn sunlight slip through the canopy, breaking into drifting columns of gold dust where moths still spiral in the last moments of their nocturnal wanderings. And there, strung between the branches of fruiting trees, hangs a vast wheel of silk, its strands glowing as though drawn from molten brass. Suspended at the hub, the golden silk orb-weaver waits with the patience of an engineer who knows her work is flawless. Her web is no simple trap, but a radiant snare carefully tuned to both physics and biology, each thread stretched to harness forces far greater than its size suggests. To watch it glimmer in the soft light of morning is to glimpse a marvel of living architecture, an invention of instinct perfected over millions of years. To understand this web, one must first learn its anatomy. The orb-weaver spins two distinct classes of silk, each with a purpose as precise as any component in a machine. From her spinnerets flow the dragline silk, the foundation threads that are taut, non-sticky, and remarkably strong. Measured gram for gram, this dragline surpasses steel in tensile strength, yet remains supple enough to bend without snapping. These draglines anchor the structure to bark and leaves, defining its frame and radiating spokes. Once the scaffold is secure, she switches glands and extrudes a different material entirely. Capture silk, designed not for strength, but for adhesion and elasticity. Where the dragline resists breaking, capture threads embrace distortion, stretching and rebounding with viscoelastic properties that make them behave like living glue. Coated in microscopic droplets that shimmer in humidity, they form the spiral of capture zones that lace between the rigid spokes. To collide with these threads is to be bound not by force alone, but by physics that favor the spider. The prey's momentum is absorbed, converted, and trapped in a net that yields without failing. The golden sheen of the web is more than ornament. It is a signal and a disguise, tuned to the wavelengths of light most visible to the diurnal insects that dominate the forest. Bees, flies, and wasps, all guided by ultraviolet reflections and yellow cues of nectar-rich blossoms, mistake the metallic strands for flowers glinting in the sun. To the human eye, the glow is subtle, a faint brass tint against the greenery, but to the compound eye of an insect, it is a beacon of promise. This deception transforms the orb-weaver's web into more than a passive trap. It becomes a lure, a false bloom suspended in mid-air. Scientists have found that under certain conditions, particularly near fruiting or flowering trees, these webs attract far more prey than colorless silk ever could. The spider has, in effect, hijacked the sensory ecology of pollinators, bending light itself into a hunting ally. Placement is everything. The orb-weaver rarely wastes silk in random locations. She reads the air currents with her legs, feeling for prevailing breezes that funnel insects along predictable flight lanes. Fruiting trees, dripping with fermenting sweetness, create convergence points where flies and bees commute in endless streams. By stretching her golden disc across these invisible highways, she inserts herself into the circuitry of the ecosystem. The web becomes not simply a structure, but a net laid across the very paths of energy flow in the forest, intercepting the transfer of sugars from plant to pollinator. Every strike is a tax collected, every capture a rerouting of energy from one species to another. When a victim collides with the sticky spiral, the encounter unfolds with mechanical precision. The web transmits vibrations like a living sensor grid, each thread resonating at slightly different frequencies depending on tension and humidity. The orb-weaver, crouched at the hub, interprets these tremors with acute sensitivity, distinguishing the frantic buzz of a fly from the heavier struggles of a beetle or the telltale flutter of a moth. Once identified, she accelerates down the spoke with a sudden drop, reel, and attack sequence. Her forelegs pin the prey as her chelicerae sink twin fangs into soft tissue, delivering venom laced with neurotoxins and digestive enzymes. Paralysis spreads quickly, immobilizing wings and legs, but subjugation is only the first step. The enzymes begin to liquefy internal organs, reducing muscle and fat into a nutrient broth. What appears to the eye as a corpse wrapped in silk is, in truth, a living reservoir of food being prepared for extraction. The silk itself is never wasted. At dawn, when the web has gathered debris, dust, and the shredded remains of wings, the orb-weaver consumes her own construction. One by one, the strands vanish into her mouth, digested into proteins that are recycled back into her glands. This routine of destruction and renewal is not indulgence, but efficiency. To build afresh without recovering resources would be unsustainable, especially when a single web requires lengths of silk many times the spider's body size. By morning's light, the disc that glowed like a sunlit medallion is gone, leaving only faint anchor lines. By dusk, another will hang in its place, tuned anew to the day's humidity and airflow. It is a cycle of building, luring, harvesting and reabsorbing, the rhythm of an architect whose material is her own body. The science of silk defies simple comparisons. Its viscoelasticity means it behaves both like a solid and a liquid, stretching under tension but snapping back to its original form. This property allows the capture spiral to arrest high-speed prey without catastrophic failure. The droplets that bead along each line are not random. They are hygroscopic, absorbing moisture from the air to maintain stickiness even as conditions shift. In high humidity, adhesion increases. In dry air, elasticity dominates, preventing brittle breakage. Insects that collide often attempt drop-to-escape maneuvers, releasing their grip on surfaces to fall free. But the web, tuned to yield without losing hold, transforms that fall into a deeper entanglement. Each thrash embeds the victim further until exhaustion hands the advantage to the spider. Even the orb-weaver's golden pigment carries functional weight. The precise chemical basis remains under study, but researchers suggest it may protect silk from ultraviolet degradation, ensuring that webs endure longer in harsh sunlight. Others note that the coloration varies between populations, hinting at local adaptations to both prey spectrum and environmental exposure. In some regions, the silk shines more intensely, perhaps reflecting higher reliance on visual lures. In others, the hue is muted, a compromise where camouflage outweighs attraction. What remains consistent is the strategic balance between invisibility to predators and visibility to prey, a paradox managed through evolution's patient refinement. To watch the orb-weaver's craft is to witness the blending of physics, chemistry, and ecology into a single act of survival. The web is a machine, but one powered by instinct rather than conscious design. It functions at scales invisible to us, capturing not only insects but energy itself, transferring calories from sunlit leaves to the body of a spider that has mastered the art of waiting. Each night's construction is a gamble against weather, against intruding birds or leaves that might tear the structure apart. Yet with dawn comes dismantling, with dusk rebuilding, the persistence of a creature that has tethered its fate to the resilience of silk. In the end, the golden silk orb-weaver is more than an ambush predator. She is a sun-net engineer, bending light, air and matter into tools of her survival. Her webs remind us that architecture need not be monumental to be profound. A wheel of silk, glimmering like brass in the morning forest, is a cathedral of tension and adhesion, a trap tuned to the frequencies of life itself. And in its glow lies a lesson that the smallest threads, spun with purpose, can hold entire worlds together. At the edge of a summer meadow, where the grasses sway like green surf under the heat of the sun, a shape breaks the continuity of stems and seed heads. Suspended in the center of an orb-shaped web, a body gleams yellow and black, striped with the confidence of danger. The wasp spider is not large compared to her insect neighbors, but her abdomen carries the unmistakable warning palette of stingers and venom, a deception meant to broadcast strength. What completes the spectacle is not the spider herself, but the structure she inhabits. Running down the web's axis is a bold zigzag band, a strip of white silk that stands out against the transparent threads around it. It is called a stabilimentum, and for more than a century it has puzzled scientists with its duality. Is it a warning tape meant to ward off larger animals, or a lure crafted to confuse and attract? Perhaps, as is so often the case in the natural world, it is both at once. To the casual observer, the stabilimentum appears decorative, an unnecessary flourish in an otherwise perfectly functional trap. Yet each strand is laid with precision, the silk thicker, denser and brighter than the rest of the web. In ultraviolet light, The spectrum to which many insects are most sensitive, the zigzag shines as though illuminated by a hidden lamp. Day-active pollinators, drawn instinctively to UV reflections that signal nectar-rich flowers, may be deceived by this bright patch and pulled toward the web's center. At the same time, birds or mammals that might blunder into the fragile net see the band as a visual cue, a warning flag that reduces accidental damage. Others suggest a simpler explanation, that the extra silk stabilizes the web structurally, reinforcing the hub against violent struggles. Each hypothesis carries evidence, yet none alone explains the whole. The stabilimentum is not a single-purpose invention, but a multi-layered adaptation, one that solves several challenges of survival in a single stroke of design. The wasp spider herself is a master of ambush. Her banded coloration, echoing the yellow and black of true wasps, is a kind of mimicry known as aposematism. Even without a sting, the illusion is powerful enough to dissuade many predators. Against the vertical green of grasses, the stripes break her outline, turning her body into a fragmented pattern that disappears when viewed from a distance. Up close, however, the effect reverses, and she becomes a vivid emblem of toxicity. This duality, camouflage from afar, threat display at close range, gives her an advantage in a habitat where visibility is both risk and opportunity. The meadow is an open world, and here survival belongs to those who can manipulate sightlines, whether to hide from danger or to invite prey into peril. Her web stretches between the stems of tall grasses, positioned with care. Unlike forest orb-weavers who hang near flowering trees, the wasp spider operates at ground level, targeting the grasshoppers and crickets that leap in abundance through the undergrowth. The design of her snare reflects this choice. The orb's vertical disc intercepts the ballistic paths of insects that bound rather than fly, a different geometry of capture. When a grasshopper collides with the sticky spiral, the impact sends a shiver across the structure, radiating through the spokes like ripples on a pond. The spider, poised at the hub, interprets the vibrations instantly. She does not wait. She sprints, accelerating down the radii with legs spread wide, her stride fluid and decisive. Upon reaching the thrashing insect, she unleashes a burst of silk from her spinnerets, encircling the victim in a cocoon that immobilizes even the strongest kicks. In seconds, the grasshopper is wrapped into a white parcel, its legs bound against its body, its power neutralized. Only then does she deliver the safety bite. Her fangs pierce the cuticle, injecting venom that subdues and preserves. The grasshopper's struggles collapse into stillness as the toxins take hold. The package, now harmless, is carried back to the hub and anchored into the web's center, stored like a ration in a larder. The stabilimentum, bold and conspicuous, now serves another role. It distracts and conceals. The bright zigzag draws the gaze, masking the outline of the bundled prey against the threads. What looked like ornament is, in truth, a multi-purpose tool, serving function after function in ways too intricate for a single explanation. The life of the wasp spider extends beyond her individual trap. In late summer, her spiderlings hatch from egg sacs and face the challenge of dispersal. The meadow cannot support hundreds of siblings clustered in one patch of grass, and so the young rely on ballooning, a behavior both fragile and astonishing. Tiny as dust motes, they climb the highest stalks and release threads of silk into the air. When the wind catches these filaments, the spiderlings are lifted skyward, becoming passengers on invisible currents. They drift for meters, sometimes for kilometers, carried to new meadows, hedgerows, or fields. This aerial exodus ensures genetic mixing and reduces competition, transforming a patch of grass into the launching pad for a continent-wide diaspora. For many, the journey ends quickly, consumed by birds, drowned in dew, or lost in barren ground. But a fraction survive, anchoring themselves in new territories where they will weave their own orbs and etch their own zigzags. The stabilimentum continues to provoke debate among biologists. Studies have shown that webs with zigzags sometimes capture more insects, but in other cases they reduce capture rates by warning prey away. Some suggest that juvenile spiders spin denser, more conspicuous stabilimenta, perhaps to avoid being destroyed by larger animals, while adults, secure in size, reduce the display to maximize hunting success. Others propose that the zigzag's true function is thermoregulation, reflecting excess solar radiation and preventing the hub from overheating. This multiplicity of interpretations mirrors the complexity of evolution itself. Traits rarely evolve for a single reason. Instead, they are shaped by overlapping pressures, each refinement adding a layer of advantage. The stabilimentum may be warning, lure, reinforcement, and thermal shield simultaneously, a silk signature that reflects the spider's negotiations with light, heat, predator, and prey. In the broader ecosystem, the wasp spider plays a quiet but significant role. By preying on grasshoppers, she helps regulate populations that would otherwise strip grasses bare. In turn, she becomes prey herself for birds, wasps, and parasitic flies that lay eggs in her body. Her life is woven into the web of the meadow, as interlinked as the threads she spins. Even her mimicry participates in this dialogue. By looking like a wasp, she not only deters predators, but also joins a larger chorus of striped insects that teach vertebrates the costly lesson of avoidance. She is part of a community of warning signals, a shared language of danger across species. To watch her at work is to see design operating on many scales at once. There is the geometry of the orb, the physics of silk, the chemistry of venom, the optics of ultraviolet reflection, and the aerodynamics of ballooning spiderlings. None exists in isolation. Each thread, each stripe, each behavior is a solution to the endless puzzle of survival. The wasp spider does not choose her patterns, but through the slow sifting of generations, her lineage has produced a body and a web that solve the problems of her habitat with remarkable elegance. And so, in the margins of fields where human eyes often glance without seeing, a drama unfolds beneath the grass tops. A banded abdomen gleams like a warning sign, a zigzag cuts a path across silk, and an unsuspecting grasshopper leaps into an invisible barrier that holds it fast. In that moment, the zigzag ceases to be mystery and becomes machinery, a functional part of a system that has endured for millions of years. Whether it warns, lures, strengthens, or blinds, the stabilimentum is a reminder that nature rarely invests in decoration without purpose. It is not a flourish. It is a strategy written in silk and sun. The desert at night is not silent. Beneath the stillness, sand shifts with the passage of beetles, and faint wing beats brush against the air as moths skim between thorn bushes. A cool wind drags across dunes that, only hours before, blazed under merciless sun. Moonlight pours silver across the ground, flattening the textures of stone and grit into monochrome. It is in this half-light that a shadow stirs near the mouth of a burrow. To the unaided eye, the creature is nearly invisible, its body blending into the soil's darkness. But under the beam of an ultraviolet torch, a different reality emerges. The scorpion's cuticle ignites with an eerie, ghostly glow, a spectral blue-green that radiates across its armored body. What looked like an ordinary patch of sand becomes a luminous apparition. This fluorescence, born of compounds embedded in the exoskeleton, remains one of biology's enduring enigmas. A phenomenon without a fully agreed purpose, thought theories abound. Some suggest it shields against UV radiation, others that it aids nocturnal vision by absorbing and re-emitting moonlight. Whatever the reason, to human eyes it transforms the scorpion into a glowing sentinel of the desert night. The black scorpion, stocky and formidable, is built like a living tank. Its body is divided into armored segments that overlap in plates, creating a flexible fortress that protects vital organs while allowing agility on uneven terrain. At the fore are the chelae, the pincers, curved and powerful, adapted for seizing prey or grappling rivals. Behind them arches the metasoma, the segmented tail tipped with the telson, a bulbous sting chamber armed with a curved aculeus. Within lies a cocktail of venom compounds, each tailored to disrupt nerve signals, paralyze muscles, or subdue struggling victims. This dual arsenal, pincers and sting, embodies a trade-off. Some scorpion species rely more heavily on brute grip, their pincers robust and crushing, while others develop slender pincers and potent venom. The black scorpion balances both strategies, wielding strength and chemistry with equal efficiency. Yet strength alone does not guarantee survival in a world of shifting sands and elusive prey. The scorpion's success lies also in its sensitivity. Along its pincers and legs sprout fine mechanosensory hairs, trichobothria, tuned to detect the faintest vibrations in air and substrate. When a beetle scrambles across sand, the tremor is relayed instantly to the scorpion's nervous system, allowing it to localize the disturbance even in complete darkness. More remarkable still is the pectine, a pair of comb-like sensory organs that extend from the underside of the body. These structures sweep the ground as the scorpion walks, sampling chemical and vibrational cues that map out territory, mark trails, and detect pheromones of potential mates. With vision limited, the scorpion reads its environment through touch and vibration, constructing a sensory landscape where every grain of sand carries information. The black scorpion is primarily a sit-and-wait predator. By day it remains hidden, tucked into burrows or under rocks, its body shielded from desiccation and heat. By night it positions itself at the burrow entrance, poised in silence, claws spread like traps. When an insect blunders near, the ambush is instantaneous. The pincers snap shut, pinning the prey before it can flee. If the victim is small, the scorpion may crush and consume it using the chelae alone, conserving venom for more demanding encounters. If the prey resists, a cricket kicking with spiny legs or a mouse attempting to bite, the tail arcs overhead in a blur, delivering a calculated sting. The venom dose is not uniform. It is metered according to context. Experiments show that scorpions adjust the amount of venom delivered depending on prey size, level of struggle, and perceived threat. Venom is metabolically expensive, a resource to be managed with precision. To sting recklessly would be wasteful. To sting judiciously ensures survival. When feeding begins, the scorpion's mouthparts, chelicerae, tear at the immobilized prey. External digestion follows, as enzymes dissolve tissues into a slurry that can be ingested. The meal is slow but efficient, leaving behind only fragments of exoskeleton. Energy is drawn from the victim into the scorpion's armored frame, fueling the cycles of molting that punctuate its life. Growth in arthropods requires periodic shedding of the exoskeleton, a vulnerable process known as ecdysis. The scorpion splits its old armor and eases free, pale and soft, before hardening into a larger instar. Each molt brings not only size, but greater strength and reproductive readiness. For days after, the scorpion avoids combat, its fresh cuticle pliable and untested. The desert, however, rarely offers reprieve, and vulnerability is the price of progress. Despite their reputation, black scorpions are not reckless aggressors toward humans. Their venom, though painful, is rarely lethal to a healthy adult, and most encounters end without a sting at all. When disturbed, scorpions often retreat into crevices or feign immobility, relying on camouflage and armor to avoid confrontation. The sting is a last resort, reserved for defense when escape is impossible. Myths of rampant aggression obscure a more nuanced truth. Scorpions are cautious animals, deeply invested in self-preservation. The glowing fluorescence that fascinates observers today likely evolved under pressures unrelated to human fear. In reality, they prefer to remain unseen, conducting their nocturnal hunts quietly beneath the radar of larger predators. One of the most striking aspects of scorpion life is the role of parental care, unusual among arachnids. After birth, the young, pale, translucent and fragile, climb onto their mother's back, clinging to her exoskeleton. There they remain, carried across the desert for days or weeks, until their first molt hardens their bodies enough for independence. During this time, the mother defends them fiercely, her body serving as both fortress and transport. The sight of a black scorpion with a brood of miniature offspring on her back is both alien and tender, a reminder that even creatures armored for war can invest deeply in the survival of their young. Each instar that follows brings them closer to the formidable autonomy of adulthood, but their first lessons in survival are learned upon the living platform of their parent. The fluorescence of scorpions remains one of nature's riddles. Some researchers argue it acts as a sunblock, filtering harmful ultraviolet rays during daytime exposure. Others propose it functions as a light amplifier, converting faint moonlight into longer wavelengths that scorpions can perceive more easily, enhancing their ability to navigate. Still others suggest it is a byproduct of cuticle chemistry, an incidental trait with no adaptive purpose at all. The truth may be layered, with benefits that shift depending on environment, life stage, and predator-prey dynamics. What is certain is that the glowing exoskeleton has become a defining hallmark, a spectral beacon that sets scorpions apart in the nocturnal desert theater. In ecological terms, the black scorpion is both predator and prey. Owls swoop silently to snatch them from the sand. Bats, guided by echolocation, can detect their movements despite attempts at stealth. Larger mammals, immune to venom, dig them from burrows as opportunistic snacks. In turn, scorpions exert pressure on insect populations, curbing outbreaks that might otherwise devastate fragile desert vegetation. Their presence is integral to balance, their nocturnal patrols part of a rhythm that links soil, plants, insects, and vertebrates. Like the wasp spider with her zigzag stabilimentum, the scorpion's strategies are woven into a larger web of interactions where survival is not merely individual, but systemic. Seen through a human lens, the scorpion is an emblem of danger, a creature that glows under black light and wields a sting. But in the ecology of the desert, it is also an engineer of balance, a parent, a strategist, and a survivor. Its armor is not aggression, but defense. Its venom not malice, but efficiency. To call it a night vision tank is to capture only part of the truth. Yes, it is armored, glowing, and armed, but it is also sensitive, deliberate, and shaped by the same evolutionary pressures that sculpt every desert life form. Its story is not one of menace, but of adaptation, a narrative written across sand and stone under the watch of the moon. The forest floor is a mosaic of decomposition and renewal. Fallen trunks, half buried in leaf litter, serve as monuments to past growth, their bark peeling away to reveal softened wood within. For many, these logs appear lifeless, but to the close observer, they are teeming with hidden activity. Inside, the architecture of decay hums with unseen miners. And crawling across the surface, clambering over ridges and crevices, is a figure instantly recognizable by its extravagant headgear, a longhorn beetle, its antennae stretching out to lengths that dwarf the body they emerge from. These paired feelers sweep like the arms of a living compass, probing, sensing, reading currents of air and vibrations of ground. If insects could lay claim to an empire of touch, smell, and spatial awareness, then longhorn beetles would be its crowned monarchs. The antennae, sometimes measuring several times the length of the beetle's own body, are not ornaments, but mobile sensor arrays of extraordinary versatility. Each segment is clothed in a landscape of sensory hairs, each hair tuned to a specific cue. Some detect volatile chemicals released by trees, the faint signatures of sap, resin, or decay. Others respond to pheromones carried invisibly through air, signaling the presence of mates or rivals. Still others act as mechanoreceptors, registering subtle changes in airflow that betray the approach of a predator or the wing beat of a nearby bird. Swept constantly back and forth, these antennae gather information from a radius larger than the beetle's body could otherwise command. They are both early warning system and navigational tool, extending perception into a three-dimensional sphere of awareness. But to understand the longhorn beetle fully, one must follow it back into the wood itself, into the hidden life of its larvae. The story begins when an adult lays her eggs on the bark of a dying or freshly fallen tree. From these eggs hatch pale grubs that burrow inward, becoming miners of cellulose and lignin. With powerful jaws, they excavate tunnels that weave through the heartwood, a process audible with the right tools. Place a contact microphone against a rotting trunk, and you may hear the faint crunching of mandibles, a rhythmic rasp that betrays their hidden presence. This acoustic chewing is more than a curiosity. It is one of the sounds of the forest recycling itself. By breaking down woody tissue, the larvae accelerate decomposition, transforming dead timber into soil and nutrients that feed the next generation of trees. What appears destructive is in fact restorative, part of a cycle that sustains entire ecosystems. For years, the larvae remain within the timber, enlarging tunnels as they grow through successive molts. Each instar deepens their commitment to the log, creating galleries that provide shelter from predators and buffer from environmental extremes. The wood itself becomes both home and food, a fortress and a larder combined. Yet this life is not without risk. Woodpeckers drill into trunks with surgical precision, guided by the vibrations of chewing grubs. Parasitic wasps probe galleries with needle-like ovipositors, delivering eggs that hatch into larvae consuming the beetle from within. Survival then is not guaranteed, but persistence ensures that some emerge, pupating within chambers and transforming into adults with armored cuticles and thyconic horns of antennae. When at last the adult longhorn beetle crawls free, its challenges shift from concealment to mobility. With wings folded beneath hardened elytra, it can take flight suddenly, launching with a clattering buzz that startles potential attackers. Its legs, long and equipped with spurs, deliver defensive kicks against those who attempt to seize it. These strikes are not delicate gestures but forceful thrusts, capable of dislodging ants, spiders, or even small lizards. Against more determined foes, chemical strategies come into play. Many longhorn beetles carry compounds derived from the plants they fed upon as larvae or adults. These chemicals are incorporated into their cuticle or secreted as deterrents, masking the beetle's scent and making them less palatable. In effect, the beetle wears the perfume of its host tree, cloaking itself in a disguise of borrowed chemistry. The cuticle itself is a marvel of defense. Smooth, rounded, and often glossy, it resists the grip of jaws and mandibles. Ant patrols, ever vigilant on fallen logs, often confront adult beetles as intruders. A clash plays out in miniature combat. The ants swarm, attempting to latch onto legs or antennae, while the beetle bulldozes forward, using sheer size and leverage toplow through. Its smooth surfaces deny purchase. Its spurred legs flick away attackers. Though the ants may harry and nip, the beetle's momentum usually carries it beyond their reach. In this, the beetle is less a duelist and more a tank, relying on armor and force rather than agility. Flight, however, is the great escape. When pressed, the longhorn beetle unfurls its membranous wings, hidden beneath the rigid forewings, and propels itself into the air. The takeoff is abrupt and noisy, a burst of mechanical energy that surprises predators with its suddenness. Though ungainly in appearance, these flights can span significant distances, allowing beetles to locate new resources, mates, or oviposition sites. The antennae, far from hindering flight, are maneuvered with care, angled to reduce drag and continue their role as navigational instruments even in mid-air. The ecological role of longhorn beetles extends far beyond their immediate survival. By consuming dead wood, their larvae create cavities that later shelter other organisms, spiders, centipedes, or solitary bees. The tunnels also admit fungi and microbes that further decompose timber, enriching soils with organic matter. In some forests, the presence of longhorn beetles is a sign of ecosystem health, a marker that recycling processes remain intact. Without them, fallen timber would accumulate, locking away nutrients and slowing the cycle of renewal. Their lives, hidden within the silence of logs, are therefore foundational to the forest's capacity to regenerate. Not all interactions are beneficial from a human perspective. Certain longhorn species target living trees, their larvae weakening timber and rendering it vulnerable to breakage or disease. Others attack stored lumber, becoming pests in economic terms. Yet even these conflicts underscore their evolutionary adaptability. The very traits that allow them to recycle fallen logs, the ability to digest lignin, to tunnel through cellulose, also equip them to exploit human-made resources. Our buildings and furniture are, to their sensory world, simply new forests of dead wood. Beyond their ecological role, the diversity of longhorn beetles is staggering. With tens of thousands of described species, they inhabit nearly every biome where woody plants grow. Some are brightly colored, mimicking wasps or toxic beetles to ward off predators. Others are cryptic, camouflaged as bark or lichen. All, however, share the defining feature of elongated antennae, a testament to the evolutionary success of this sensory empire. For these beetles, perception is power, and their survival hinges on the reach and refinement of those sweeping appendages. To witness a longhorn beetle navigating a rotting log is to glimpse a balance of strength, patience, and sensory mastery. Each movement of its antennae sketches an invisible map of chemical trails, air currents, and potential threats. Each step across decaying bark participates in a story of decomposition that ultimately nourishes the forest itself. In moments of conflict, a sudden swarm of ants, a probing predator, it reveals its arsenal of defenses, armor, spurs, wings, and disguise. And yet, despite its formidable appearance, the beetle is no predator of menace. It is a recycler, a custodian of fallen giants, turning the death of trees into the soil of tomorrow. The longhorn beetle's antenna empire is not simply a matter of extravagance. It is an empire built upon information, upon the ability to sense a world too subtle for human eyes or ears. Through these sweeping instruments, the beetle commands awareness that stretches far beyond its small body, allowing it to navigate, survive, and fulfill its ecological role. In the quiet decay of the forest floor, where trunks collapse and fungi bloom, the longhorn beetle reigns not with claws or venom, but with perception stretched to improbable lengths. On a warm spring morning, the garden comes alive with quiet industry. Sap rises in tender shoots, and clusters of aphids pierce the green veins, their needle-like mouthparts siphoning the plant's energy. The aphids swell with sugary sap until their bodies glisten translucent, a living herd feeding endlessly. Ants march along the stems, stroking the aphids with their antennae to harvest honeydew, the sweet liquid excreted by their charges. For the ants, it is livestock management. For the plants, it is parasitic drain. And into this tableau rolls an unmistakable figure, a small, bright dome of crimson marked with black, a beetle that moves with deliberate confidence. The ladybug, familiar to children and farmers alike, is about to reveal why its cheerful appearance conceals a predator's efficiency. The ladybug's coloration is not decoration but advertisement. Red wings dotted with black are signals in the universal language of aposematism, a warning of chemical defenses. Beneath its glossy cuticle, the ladybug stores alkaloids that are bitter and sometimes toxic, distasteful enough to convince birds or lizards that a single bite is not worth repeating. Should a predator ignore the warning and attempt to seize it, the beetle has another defense. At the joints of its legs, it can exude droplets of hemolymph in a process called reflex bleeding. These yellow-orange beads carry the same acrid chemicals, spreading a stench that clings to beak and tongue. To the attacker, it is a lesson delivered in unpleasant taste, a deterrent more powerful than armor or sting. In the economy of survival, the ladybug's colors and secretions broadcast one message: approach at your peril. This reputation for being unpalatable grants the ladybug a freedom to hunt in open view. On the aphid-laden stems, it behaves like a red bulldozer, plowing through clusters of soft-bodied insects with slow, relentless intent. Each movement of its mandibles is precise and methodical, seizing one aphid after another, crushing them into nutrient-rich meals. An adult ladybug can consume dozens in a single day, and over the course of a lifetime, thousands. Its appetite is not casual grazing, but ecological service. By thinning the aphid populations that threaten crops and gardens, ladybugs act as allies to farmers and gardeners across the world, assassins disguised as ornaments. But the true devastation is not wrought by the adults. It comes from their offspring, born into landscapes already mapped with food. The female selects oviposition sites carefully, laying her eggs near dense aphid colonies. Each cluster of pale, yellow-orange eggs is a tactical deployment, positioned so that the larvae will encounter prey the moment they emerge. When they hatch, the young are unrecognizable compared to their round, cheerful parents. They resemble miniature alligators, elongated and bristled with spines, colored in mottled black and orange. These larvae are restless predators, armed with sickle-shaped mandibles and an insatiable drive to feed. Aphids, adapted for rapid reproduction, multiply at astonishing rates. Many species bypass mating altogether, producing live clones in cycles that can double populations within days. Left unchecked, They blanket stems and leaves, draining plants into wilted ruin. Ladybug larvae are the countermeasure evolution has placed in their path. Each larva can consume hundreds of aphids in the weeks before pupation, their spiky silhouettes patrolling stems with tireless hunger. They seize prey in quick strikes, pierce bodies, and drain them with ruthless efficiency. If food is scarce, they do not hesitate to turn cannibal, consuming unhatched siblings or weaker larvae. In this brutal arithmetic, only the strongest reach adulthood. The rhythm of these outbreaks is tied to the plants themselves. When sap flows are abundant, aphid populations surge, providing a feast for ladybugs. Their reproductive cycles respond in turn, with more eggs laid and more larvae emerging to reap the bounty. Predator and prey rise and fall together in pulses that ripple through the growing season. Farmers may see this as biological pest control, but to the beetle it is simply survival. The synchrony of plant, aphid, and ladybug is a triad of dependence and conflict, a reminder that ecological balance is written not in absolutes, but in shifting pressures. Adult ladybugs, despite their martial diets, are not bound exclusively to carnivory. Some supplement with pollen, nectar, or fungal spores when insect prey is scarce. This flexibility allows them to survive lean periods, sustaining energy until aphid colonies return. Their diet is a spectrum, but their role as aphid assassins remains their most celebrated contribution. Even so, they remain vulnerable. Parasitic wasps insert eggs into their bodies, turning them into living hosts for larvae that consume them from within. Fungal pathogens strike in damp weather. Birds and frogs, immune to aposematic warnings, occasionally ignore the chemicals and eat them regardless. Bright colors offer protection, but no strategy guarantees invulnerability. As autumn draws near and prey dwindles, ladybugs prepare for a very different challenge: survival through winter. Unlike many insects that die off at season's end, leaving only eggs for spring, ladybugs enter diapause, a suspended state of low metabolism that allows them to endure months of cold. To do this, they seek shelter in numbers. Cues of shortening daylight and falling temperatures trigger aggregation behaviors, drawing thousands of individuals into communal refugees. They gather in cliff crevices beneath bark and, much to human surprise, inside houses and attics. Walls and window frames bloom with orange-red clusters, beetle upon beetle packed tightly together, their combined bodies forming living insulation. These aggregations are more than convenience. By clustering, ladybugs share warmth and reduce water loss, their collective presence increasing survival rates compared to solitary hibernators. The spectacle is striking. Once solitary predators transformed into orange mosaics, carpeting surfaces in quiet dormancy. To the casual observer, it may seem an invasion. To the beetles, it is simply a seasonal strategy, a way to pass the inhospitable months until aphids once again bloom on spring shoots. When warmth returns, the cluster dissolves. The assassins disperse, returning to fields and gardens ready to repeat the cycle. The ladybug story reveals the paradox of scale in ecosystems. A creature barely the size of a fingernail exerts influence far beyond its body weight. By curbing aphid populations, ladybugs safeguard plant vitality, indirectly supporting the food webs that extend to birds, mammals, and humans. Their chemical defenses, larval predation, and communal overwintering strategies illustrate the diversity of tools evolution equips even the smallest of species. They are reminders that biological warfare does not require size, only efficiency and adaptation. In a field of aphid herds tended by ants, the arrival of a single ladybug can shift the balance of power. Ants scatter in alarm as their sugary livestock vanish into mandibles. The bright dome rolls forward, implacable, undeterred by numbers. The aphids, defenseless, fall in droves. And when the last leaf curls under the weight of their feeding, when the plant itself begins to suffer, it is the ladybug that restores balance, not for altruism, but for survival. Yet in this convergence of needs, farmers and beetles find themselves unlikely allies, their fates joined by the destruction of a common enemy. So when thousands of ladybugs cluster in winter dormancy, forming orange walls in forgotten attics, it is worth remembering the role they play. These are not mere decorations of nature, but assassins in miniature, their lives bound to cycles of prey and season. In their bright shells and spiky larvae lies a story of predation, defense, and endurance, the tale of a small beetle whose presence keeps the green world in balance. On a quiet summer afternoon, when sunlight presses hot against the eaves of barns and garden fences, a faint rasp carries from the wood. Look closely, and a perfect round hole comes into focus, as if a craftsman had pressed a drill bit into the beam. The edges are smooth, the circle precise, the tunnel vanishing into darkness. It is not the work of tools, but of mandibles. This is the signature of the carpenter bee, an insect both admired and misunderstood, known for its ability to carve into dead wood and its indispensable role as one of nature's most powerful pollinators. Step into the tunnel, and the gallery unfolds like a blueprint of instinct. The entrance leads into a corridor that runs parallel to the grain of the wood, the walls polished smooth from repeated passes of the bee's jaws. Along this hallway, the female constructs nursery cells by partitioning the gallery with walls of chewed wood pulp, each chamber a cradle for a single offspring. Within each cell, she places a mound of pollen bread, a mixture of pollen grains and nectar kneaded into a protein-rich loaf. On this provision, she lays one egg, sealing the chamber before moving deeper to repeat the process. The architecture is functional and linear, a series of rooms arranged with care, the future of the next generation, stored in edible vaults of gold and sugar. But it is outside the wood that carpenter bees perform their most extraordinary work. Among flowering plants, they engage in a behavior that borders on the violent, buzz-pollination or sonication. Many blossoms, particularly those of tomatoes, blueberries, and eggplants, conceal their pollen within tubular anthers that do not release grains freely. For most insects, these flowers are a locked pantry, inaccessible despite their abundance. Carpenter bees, however, have evolved the key. Gripping the flower with their jaws, they disengage their wings and fire their flight muscles at full force, vibrating their thorax with extraordinary intensity. The entire flower trembles in their grasp, and pollen erupts in clouds, dusting the bee's body in a golden mist. What looks like aggression is a precise adaptation, a way to extract resources hidden from less determined visitors. In ecosystems and in agriculture alike, this vibration unlocks fertility, ensuring the pollination of crops that humans depend upon. The physics of this sonication is a marvel of biology. Carpenter bees vibrate at frequencies tuned to resonate with the flower's structure, amplifying the release of pollen. In effect, they shake the plant into giving up its treasure, using energy generated by flight muscles without the expense of flight itself. Other bees, including bumblebees, share this ability, but carpenter bees are among its most proficient practitioners. Without them, many crops would yield poorly, and wild plant communities would lose an essential link in their reproductive chain. In a world where pollinators are in decline, these vibrating locksmiths remain crucial custodians of food security and biodiversity. Carpenter bees often draw human attention for less celebrated reasons. Their penchant for drilling into wood beams earns them suspicion as structural pests. Yet their behavior is more nuanced than their reputation suggests. They prefer dead, unpainted or weathered wood, targeting natural timber rather than actively damaging sound, painted lumber. Unlike termites, they do not eat wood but excavate it solely for shelter and nesting. In most cases, their impact on buildings is cosmetic rather than catastrophic, the tunnels shallow and limited in scope. The true ecological story lies not in the holes they make in barns, but in the fertility they bring to fields and orchards. To brand them as ruinous is to miss their greater role as ecosystem engineers. The bees themselves exhibit a fascinating balance of defense and restraint. Males, with their large size and conspicuous hovering near nest entrances, often intimidate observers. They dart toward intruders, patrol territories, and defend invisible boundaries with remarkable persistence. Yet their ferocity is bluff. Male carpenter bees lack stingers altogether, their aggression a theater meant to deter rather than to harm. The females, by contrast, carry functional stingers but are reluctant to use them. Unless handled or severely provoked, they avoid stinging, investing instead in the labor of foraging and construction. Their strategy is one of efficiency, reserving energy for survival tasks rather than wasted combat. The life cycle of carpenter bees reflects both vulnerability and resilience. Eggs hatch into larvae that feed on the pollen bread provisions within their wooden cells. They grow in darkness, protected by partitions, until pupation transforms them into adults. When they emerge, they inherit not only the tunnel, but also the responsibility of continuing the cycle of drilling, provisioning, and pollinating. Some reuse old galleries, extending them deeper into wood, while others carve fresh passages. In this continuity, carpenter bees participate in a slow reshaping of the wooden world, turning timber into both shelter and legacy. The ecological ripple of their actions extends far beyond the nest. By sonicating flowers, they enable fruit set in species that would otherwise fail to reproduce effectively. Their bodies, dusted in pollen, become vehicles of gene flow, bridging plants across distances and maintaining genetic diversity. Their tunnels, though maligned in buildings, also provide habitats for other organisms. Abandoned galleries can house solitary wasps, spiders, or other insects seeking refuge. In this way, carpenter bees shape ecosystems not only through pollination, but also through the physical architecture of their nests. Carpenter bees also face predators and parasites. Woodpeckers pry into galleries, drawn by the sound of larvae within. Parasitic flies and wasps deposit eggs at nest entrances, their larvae infiltrating the provisions meant for bee offspring. Spiders capture adults on flowers, their webs positioned with surgical precision along flight paths. Despite these pressures, carpenter bees persist, their adaptations honed to balance risk with reproduction. Their persistence ensures the survival not just of their lineage, but also of the plants that rely on their unique skill set. From an evolutionary perspective, the carpenter bee exemplifies the trade-offs that define survival. By investing in powerful mandibles and vibration-tuned muscles, it has secured access to resources denied to many others. By risking exposure with conspicuous drilling and open foraging, it has earned both ecological prominence and human suspicion. By balancing aggression with restraint, it has created a strategy where survival does not require constant conflict. These choices, shaped over millions of years, reveal an insect whose role in ecosystems cannot be reduced to pest or pollinator alone, but must be understood as both. As autumn approaches, carpenter bees slow their activity. Some seek shelter within the very galleries they or their ancestors carved, overwintering in the wood until warmth returns. Others die, leaving their progeny sealed in nursery cells to continue the cycle. Winter stills their buzzing muscles, but spring reignites them, and once again they return to wood and flower, drill and vibrate, carve and pollinate. Their story is not one of destruction, but of persistence, written in round doorways and clouds of pollen. Seen through the narrow lens of human concern, carpenter bees may appear as nuisances, their tunnels blemishing beams and rails. Yet in the broader lens of ecology, they are indispensable allies, locksmiths of fertility whose vibrations feed both wildlife and human harvests. Without their sonication, many flowers would remain locked, their pollen inaccessible, their fruits unrealized. The carpenter bee reminds us that even the smallest vibrations can reverberate through ecosystems, shaping forests, farms, and the very meals on our tables. In the macro view of a wood beam, a small round hole is not merely damage. It is an entrance to a nursery, the mark of an architect whose tools are her own jaws. In the field, a trembling flower is not merely shaken but unlocked, its future carried in pollen grains dusted across the bee's body. And in the human imagination, the carpenter bee is not only a buzzing intruder, but a vital partner in the survival of plants and the fertility of landscapes. These vibrating locksmiths, with their round doors and resonant thoraxes, are guardians of a cycle older than agriculture itself, a cycle of drilling, buzzing, and renewal that keeps life flowing from flower to fruit. At the edge of a woodland clearing beneath the eaves of a shed, a strange architecture emerges from shadow. It hangs like a grey lantern, its walls rippled and striated, the whole structure delicate yet resilient. Draw closer and the builders are revealed, slender-bodied wasps, their yellow and black stripes glinting in the sun as they ferry slivers of wood to the hive. With their mandibles, they scrape fibers from fence posts and fallen branches, chewing the fragments into pulp and mixing them with saliva. From this paste, they sculpt paper, layering it into thin, papery sheets that form the walls of their nest. What begins as a single stalk and a small umbrella of cells expands into a vast colony, tier upon tier of hexagonal comb, each chamber aligned with remarkable precision. The geometry of these combs is no accident. The hexagon, repeated endlessly, is the most efficient shape for housing brood while minimizing wasted material. Each wall supports the next, distributing weight evenly, allowing the wasps to stretch their resources to the maximum. Within the cells, eggs hatch into larvae that curl like pale grubs, tended by the tireless efforts of workers. These larvae are the future of the colony, and the entire society is organized around their care. Protein gathered from the outside world, chewed insect prey or fragments of meat, is delivered into their waiting mouths. In return, the larvae secrete sugary droplets that nourish the adult workers. This reciprocal exchange forms the basis of wasp society. The young feed on animal flesh, the adults feed on sugar, and together they maintain the balance of the nest. Temperature regulation within this paper city is an art of collective physiology. On hot days, workers line the nest entrance and fan their wings in unison, directing cooling breezes into the chambers. In cooler conditions, they huddle together, bodies vibrating to generate heat. The brood must be kept within a narrow thermal range for proper development, and the colony achieves this without instruments, relying instead on instinctive coordination. To an observer, the nest hums not only with wing beats, but with the rhythm of a living organism. Each wasp a cell in a superorganism that breathes, sweats, and regulates as one. Outside the nest, the roles of foragers become visible. Some scour flowers and tree sap for sweet liquids, fueling the energy needs of adults. Others patrol shrubs and grass, hunting for prey to deliver to the larvae. A wasp in hunting mode is a specialist predator, agile and unflinching. She lands on a leaf where a caterpillar feeds, her antennae sweeping, her compound eyes locking onto the target. With a sudden lunge, her mandibles seize the writhing body and the struggle is brief. Rather than consume it immediately, she begins to dismantle it with precise efficiency, stripping the soft tissues into manageable strips. These pieces are carried back to the nest, still fresh, destined for the hungry mouths of developing larvae. In this way, wasps exert a powerful influence on insect populations, curbing outbreaks of caterpillars and other herbivores that could devastate plants. The sting, of course, is their most infamous weapon. At the tip of the abdomen lies the ovipositor, repurposed by evolution into a hypodermic needle. Within it courses a venom that contains both neurotoxins and enzymes, capable of paralyzing prey and inflicting searing pain on larger animals. Yet the wasp does not always kill outright. In laboratory demonstrations, prey injected with venom remain alive but immobilized, their muscles silenced while their organs continue to function. For larvae, this provides a gruesome advantage, fresh meat that does not rot. To the human eye, it may seem cruel, but in ecological terms it is efficiency, preservation without refrigeration, storage by paralysis. For the colony, defense is as critical as foraging. Wasps live in societies that can number in the thousands, and the loss of a nest would mean the death of an entire generation. To guard against threats, they have evolved alarm pheromones, chemical signals released when a wasp is injured or angered. One sting is not an isolated act. It becomes a chemical beacon, rallying nearby workers to the attack. This is why a single swat can escalate into a swarm. The pheromone lingers in the air and on skin, marking the target for multiple assaults. To humans, it feels like vengeance. To the wasps, it is a coordinated defense strategy, a communal response that ensures the survival of the nest even at the cost of individual lives. Despite their reputation, wasps are not mindless aggressors. Most interactions end without incident. Foragers at flowers often ignore human presence unless directly threatened. Their stings are weapons of last resort, reserved for defense rather than offense. Indeed, the energy expended in producing venom and the risk of injury in combat mean that aggression is costly. Only when the nest itself is threatened does the full fury of collective defense erupt. In this way, wasps embody a principle found throughout animal societies: protect the home at all costs, tolerate the world when possible. The architecture of wasp nests varies across species. Some are modest, a single comb suspended beneath a leaf, tended by a handful of workers. Others grow into massive, layered spheres that can fill the hollows of trees or the corners of attics. Each reflects the same principle of paper construction, fibers transformed into fortress. Unlike bees, wasps do not store honey. Their societies are seasonal, rising in spring when a solitary queen begins her first comb, swelling through summer as workers multiply, and collapsing in autumn as frost claims the workers and only fertilized queens survive. These queens overwinter in bark crevices or soil, emerging when warmth returns to begin the cycle anew. The grand paper cities are temporary, dissolving each year, yet the species persists through the resilience of its queens. Ecologically, wasps serve as both predators and pollinators. While their hunting suppresses insect populations, their visits to flowers transfer pollen inadvertently, supporting plant reproduction. They are generalists, connecting multiple trophic levels, their impact felt across ecosystems. To gardeners and farmers, they are both feared and appreciated, their stings remembered but their pest control services often overlooked. Without them, landscapes would be overrun by herbivorous insects, and many plants would lose an important, if imperfect, pollinator. Seen in close perspective, the wasp reveals contradictions. It is an architect that builds with delicacy, yet a warrior armed with venom. It is a caregiver that feeds its larvae with precision, yet a predator that dismantles prey alive. It is a communal being that thrives only in society, yet whose individuals may sacrifice themselves in defense of that society. These contradictions are not flaws, but the essence of its survival strategy. The paper city is more than a nest. It is a crucible where cooperation, aggression, and resilience converge. As summer deepens, the hum of a wasp colony becomes the soundscape of meadows and gardens. Wing beats blur the air, workers shuttle between nest and field, and larvae swell within their paper cradles. To the casual observer, the sight of a wasp near a picnic stirs only caution. Yet behind that encounter lies a story of engineering, predation, and social complexity. A wasp is not merely a stinger, but a builder of cities, a regulator of ecosystems, a creature whose survival strategies mirror the sophistication of any engineered society. In the end, to understand wasps is to look past fear and into function. The perfect hexagons of their combs, the synchronized fanning of their wings, the surgical dismantling of prey, the chemical alarms that unite them in defense, all are chapters in the story of survival written in paper and venom. Their cities may crumble with the first frost, but their legacy endures, rebuilt each spring in fibers chewed from wood and bound with saliva. Paper cities, precision stings, a society measured in cycles of birth and dissolution. The wasp is both builder and soldier, and in its world those roles are inseparable. At the boundary where city pavement meets the roots of trees, life adapts in unexpected ways. In the cracks of sidewalks, beneath benches, and along the warm bases of sunlit walls, clusters of small insects gather in masses that look almost like spilled paint. Their bodies are bright red, crossed with bold black markings that resemble masks and shields. To children, they are a curiosity, harmless, almost decorative. To ecologists, they are a window into how even the simplest insect societies manage heat, reproduction, and survival in environments shaped by humans. These are firebugs, the red marchers of the sidewalk, and though they lack stingers, venom, or dramatic predatory skills, their story is rich with adaptations that allow them to flourish in a world shared with us. Seen from above, their aggregations are striking. Dozens, sometimes hundreds, cluster together on sun-facing walls or at the bases of linden trees, their bodies pressed close in carpets of crimson and black. This gathering is not random. Firebugs are ectotherms, their internal body temperatures governed by the warmth of their environment. By clustering together in large groups, they create microclimates, sharing and amplifying heat absorbed from the sunlit ground. This collective thermoregulation allows them to warm quickly on cool mornings and to extend their activity into seasons when solitary insects would remain dormant. The sight of a sidewalk wall alive with red speckles is therefore more than spectacle. It is survival through social sunbathing. Though they resemble beetles at first glance, firebugs are true bugs, belonging to the order Hemiptera. Their defining feature is not jaws, but a piercing sucking mouthpart called a rostrum, folded beneath the head when not in use. With this syringe-like instrument, they tap into seeds, drawing out liquid nourishment rich in sugars and oils. Linden trees, mallows, and hibiscus provide much of their sustenance, as fallen seeds scattered across urban soil become a banquet for their probing beaks. This feeding style makes them scavengers rather than plant destroyers. Contrary to urban myth, they do not harm living trees or chew wood. They exploit the surplus of fallen seeds, tidying the ground in the process. Watch closely as one feeds. The rostrum pierces the seed coat with patient pressure, slipping into the nutritious endosperm inside. Saliva, injected in minute amounts, liquefies the tissue, making it easier to draw upward through the slender tube. The process is slow, meticulous, but efficient. A seed may be tapped by several individuals in succession, each drawing what it can before the husk is discarded. This style of feeding links them to other true bugs such as aphids and cicadas, all of which rely on fluid meals rather than chewing. What unites them is precision, the ability to turn plant tissue into drinkable sustenance through chemistry and mechanics. Firebugs are not strictly limited to seeds. They scavenge opportunistically, probing dead insects or other organic material. Their diet is flexible, one reason they thrive in city habitats where food is inconsistent. A dead bee on the pavement, a cracked seed in the dust, all are potential resources. This adaptability makes them successful colonizers of urban edges, where other insects struggle with fragmented habitats and unpredictable resources. Perhaps their most endearing, if curious, behavior is their courtship. During spring and summer, pairs of firebugs can be seen attached end-to-end, moving awkwardly across sidewalks like miniature trains. This tandem arrangement is the result of prolonged copulation, which can last for hours or even days. In this position, male and female remain locked together, their abdomens fused as they move in reluctant cooperation. The evolutionary advantage is debated, but prolonged attachment likely ensures paternity by preventing rival males from mating with the female immediately after. To human observers, the sight of firebug pairs dragging one another across warm pavement is almost comical, but it represents a serious investment in reproductive security. The life cycle of firebugs follows the familiar pattern of gradual metamorphosis, distinct from the complete transformations of butterflies or beetles. Eggs are laid in soil or under leaf litter, often near the base of host plants. From these emerge nymphs, which resemble small, wingless versions of the adults. Over successive molts they grow larger, their coloration intensifying, wings developing gradually until they reach full maturity. At each stage they remain gregarious, clustering together in aggregations that provide protection through numbers and warmth. These nymphs are often more vividly red than adults, their markings simpler, which may serve as a visual deterrent to predators that associate bright coloration with unpalatability. Though they lack potent toxins or venom, firebugs are not entirely defenseless. Their coloration alone functions as a mild warning, a posmatism by suggestion. Birds that have sampled bitter-tasting true bugs often learn to avoid red and black insects in general, granting firebugs a measure of protection through mimicry. They also release mild defensive chemicals from glands in their abdomen, producing odors that discourage would-be predators. While not as dramatic as the reflex bleeding of ladybugs or the sting of wasps, these modest defenses are sufficient when combined with group living. Predators may pick off a few, but rarely wipe out an aggregation entirely. Their presence at the base of linden trees is particularly notable. These trees drop vast numbers of seeds, especially in city plantings where they line boulevards and courtyards. The firebugs exploit this abundance, their populations swelling in synchrony with seed fall. Urban landscapes, with their ornamental mallows and hibiscus, provide additional food sources, creating habitats tailored almost inadvertently for their needs. In this way, human cities have become extensions of their natural range, offering heat-retaining walls, seed-rich pavements, and predator-free refuges. Yet firebugs also serve ecological roles beyond scavenging. By consuming fallen seeds, they influence plant recruitment, reducing the number of seeds that germinate beneath parent trees. They also provide prey for birds, spiders, and predatory insects, linking the flow of energy from seeds upward into higher trophic levels. Their aggregations, though dense, are temporary, dispersing when resources are depleted or temperatures shift. What appears to be a static carpet of red is in fact a dynamic system of arrivals and departures, a fluid colony without central organization. In winter, firebugs seek refuge in leaf litter, bark crevices, or beneath stones, entering diapause to survive the cold months. With spring warmth, they re-emerge, often in large numbers at once, giving the impression of sudden population explosions. In truth, they are simply resuming activity after months of dormancy, synchronized by environmental cues. Their survival strategy is not unlike that of ladybugs clustering in attics, though firebugs remain closer to soil, their aggregations spread across the urban landscape. To many city dwellers, firebugs are among the most visible insects of daily life. They are encountered not in forests or meadows, but on sidewalks and walls, cohabiting with us in plain view. Their harmlessness makes them approachable, their aggregations easy to observe without risk. In this accessibility lies an opportunity. They are ambassadors of entomology, introducing people to the complexity of insect life at the very edge of human habitation. A child watching a pair shuffle across the pavement or a cluster bask against a wall is witnessing thermoregulation, reproductive strategy, and social behavior in action, lessons in ecology delivered on the most ordinary stage. Seen with patience, firebugs reveal how even modest insects embody intricate adaptations. They regulate their temperature through group living, feed with syringe-like precision, secure reproduction through prolonged pairing, and exploit human-made habitats without conflict. They remind us that survival is not always about ferocity or venom, but about timing, flexibility, and cooperation. On a warm afternoon, as the city hums with traffic and footsteps, a quiet drama plays out at ground level. Red marchers cluster in the sun, pairs shuffle awkwardly across pavement, and seeds are tapped with delicate syringes. These firebugs are neither pests nor heroes, but participants in the urban ecosystem, small scavengers that thrive in cracks and courtyards where nature meets stone. In their persistence, they show how life adapts to the margins of human structures, turning sidewalks into stages of survival. The story begins on the underside of a milkweed leaf, where a tiny egg clings like a droplet of ivory glass. Within its fragile shell, a caterpillar coils, waiting for the moment when jaws, sharpened by evolution, will pierce the only food it will ever accept. Days later, the shell cracks, and a striped larva emerges, black, white, and yellow bands wrapping its body like warning tape. It wastes no time. The newborn immediately turns to eat the very leaf that bore it, beginning a life fueled entirely by milkweed. These plants are not chosen by accident. They contain cardenolides, bitter chemical defenses potent enough to sicken vertebrates. Yet for the monarch caterpillar, these toxins are both shield and inheritance. Incorporated into its tissues, they become a lifelong defense, eventually carried into adulthood and displayed on wings of blazing orange. As the caterpillar grows, it devours leaf after leaf, molting through successive instars until it swells many times its hatching size. Its mandibles scrape edges into crescents, leaving signature arcs on the milkweed's foliage. Every few days, the caterpillar splits its skin, wriggling free from a tighter exoskeleton to reveal a larger form beneath. These moments of vulnerability are short-lived, and feeding resumes almost immediately. In fields where milkweed grows unchecked, the sound of soft chewing can be heard by those who listen closely, a quiet rhythm of survival. At last, when the caterpillar has reached its final instar, a transformation begins that is almost beyond imagination. The larva attaches itself to a stem or leaf with a silk pad and hangs upside down in a J shape, its body quivering with unseen changes. Hours later, the skin splits one final time, but instead of a larger caterpillar, a jade-green chrysalis emerges, studded with gold flecks that shimmer like metal leaf. Inside, the body dissolves into a cellular soup, tissues broken down and reorganized. Out of destruction comes reassembly, wings form, antennae develop, and the simple gut of the caterpillar is replaced with the complex systems of an adult butterfly. It is a time-lapse miracle, a metamorphosis hidden behind walls of living jade. When the chrysalis finally splits, the monarch butterfly emerges, crumpled, damp, fragile. Over the next hours, hemolymph is pumped through its wings, expanding them to their full spread. As they dry, they harden into panels of fiery orange, laced with black veins and bordered with white spots. These wings are more than decoration. They're advertisements of toxicity, a signal to birds that this butterfly carries the cardenolides it consumed as a caterpillar. For predators that ignore the warning, the lesson is unforgettable: nausea, vomiting, or even death in smaller animals. The monarch's color is both beauty and deterrent, a flag of survival unfurled across the sky. Yet the monarch's story stretches far beyond metamorphosis. It is a tale of movement across continents, a migration so vast and improbable that it has puzzled scientists for decades. Each autumn, monarchs in North America embark on a journey from Canada and the northern United States to the highland forests of central Mexico. No individual makes the round trip. Instead, the migration is a relay of generations. Butterflies that leave Mexico in spring fly northward, breed and die, passing the baton to their offspring. These in turn continue the journey, advancing further across the continent. By the time monarchs return to Mexico in autumn, they are the great-great-grandchildren of those that departed. And yet, with no guides but instinct and environment, they arrive at the same groves of oyamel fir trees, clustering in the millions on trunks and branches. How do creatures with brains smaller than a pinhead navigate such distances? Science has uncovered several keys. Monarchs use a sun compass, orienting themselves by the position of the sun in the sky. But because the sun shifts through the day, they pair this with an internal circadian clock, allowing them to correct their angle of flight as time passes. This dual system, solar compass plus biological timekeeper, guides their southward trajectory. On cloudy days when the sun is obscured, evidence suggests that monarchs rely on Earth's magnetic field as a backup, a geomagnetic sense that ensures orientation when light fails. Together, these tools create a navigational suite that rivals those of migratory birds or sea turtles, allowing a paper-thin insect to cross thousands of kilometers with uncanny accuracy. The migration itself is filled with hazards. Storms batter wings, leaving them ragged. Roads and cities fragment habitats, forcing butterflies to cross inhospitable stretches where nectar is scarce. Predators exploit the journey. Birds in Mexico, having evolved resistance to cardenolides, feast on the arriving swarms. And yet, the population endures, its strength not in the longevity of individuals, but in the continuity of generations. What one cannot complete, another will carry forward. The compass is not of a single butterfly, but of a lineage, encoded in genes and behaviors passed down through countless cycles of metamorphosis. Milkweed, the plant on which monarchs depend, is central to this odyssey. Without it, there can be no caterpillars, no toxins to store, no new generations to continue the journey. Yet milkweed has been stripped from roadsides and fields across much of North America, casualties of herbicide use and land development. Conservationists now encourage its planting in gardens and along highways, creating stepping stones for migrating monarchs. The choices humans make in agriculture and landscaping ripple into the survival of these butterflies, shaping the fates of migrations that span continents. On their southward return, monarchs gather in densities that transform forests into living mosaics. Trunks vanish beneath layers of overlapping wings. Branches sag under the collective weight of millions of insects. In the cool mountain air, the butterflies enter a state of torpor, conserving energy through the winter. When warmth returns in spring, they rouse, mate, and begin the cycle again, heading north to spread across the continent. The continuity is fragile, dependent on climate, habitat, and the synchronized survival of each link in the chain. Beyond their biological marvels, monarchs carry cultural significance. For many in Mexico, their arrival coincides with the Day of the Dead, and they are seen as the returning souls of ancestors, migrating with the seasons of remembrance. In scientific laboratories, they serve as models for understanding circadian rhythms and navigation. In classrooms, they are often a child's first introduction to the wonder of metamorphosis, a story of change written in wings. And so, from a single egg on a milkweed leaf to a continent-spanning migration, the monarch butterfly reveals the power of small lives linked by cycles of transformation and movement. Its compass is not mechanical but biological, calibrated by sun, time, and magnetism. Its shield is borrowed from the toxins of its host plant, advertised by the brilliance of its wings. Its survival depends not only on instinct, but on the landscapes we choose to shape and protect. On a warm morning in Mexico, in forests of oyamel fir, the air is alive with the sound of rustling wings. Millions of monarchs rise at once, their orange clouds drifting into the sky like living embers. Each butterfly, fragile on its own, is part of something larger, a migration that binds generations into a single continuous journey, a compass written on leaves and carried in wings. The forest floor is a world in miniature, a dim underlayer of leaf litter, rotting wood and soil where life hums unseen beneath our feet. Sunlight fractures through the canopy above, but here in the shadows, the air is cool and damp, carrying the smell of decay and renewal. Ant columns run like living highways through the detritus. Beetles burrow into softened logs. And among them, slow and deliberate, a pill millipede navigates the labyrinth of leaves, its glossy shell catching what little light filters down. At first glance, it resembles the familiar woodlouse, the roly-poly children often cup in their palms. But closer inspection reveals an older lineage, not a crustacean but a true millipede, armored and multi-legged, adapted to survive in the perpetual twilight of the soil. The pill millipede carries its body low, supported by dozens of legs that ripple in coordinated waves. Each step is small, but together the movement is steady, a conveyor belt of motion pushing the animal forward through debris. Unlike the elongated ribbon-like millipedes that coil into spirals when disturbed, this species has evolved a different strategy. Its body is short, oval, and segmented into domed plates that hinge neatly together. When threatened, it performs conglobation, the act of rolling into a perfect sphere. The plates lock tightly, the head and legs tucked completely within until nothing remains but a smooth, sealed ball of armor. To an ant or spider, the transformation is baffling. Where once there was a vulnerable, many-legged creature, there is now a pebble, impenetrable and unyielding. This defense is not mere bluff. The surface of the pill millipede's armor can exude chemicals, primarily benzoquinones, from tiny pores. These compounds are acrid and irritating, enough to burn the mouthparts of ants or deter the probing palps of spiders. In some species, the chemicals leave visible stains on soil, a faint trace of the millipede's chemical arsenal. Predators quickly learn that the glossy spheres are not worth the effort. Even vertebrates, such as shrews or small mammals, often spit them out after a single attempt. The pill millipede wins not through speed or aggression, but by being unpleasant to attack. Its armor and chemistry, a combination of physical and chemical deterrence. Yet its story is not only one of defense. Pill millipedes are recyclers, indispensable to the forest. Their diet consists primarily of decaying leaves, wood fragments, and organic detritus. Using mouthparts adapted for grinding, they consume material that would otherwise linger in the litter layer. Within their guts, microbial symbionts assist in breaking down complex compounds, particularly lignin and cellulose, transforming tough plant matter into smaller particles. The millipede's digestive system becomes a processing unit, turning leaf litter into enriched soil. What enters as coarse debris exits as nutrient-rich pellets that nourish fungi, plants, and countless soil organisms. Without such recyclers, forests would choke on their own debris, the cycle of nutrients slowed to stagnation. Their role in moisture cycling is equally vital. Pill millipedes are highly sensitive to desiccation, their bodies designed for damp habitats. They emerge mostly at night or after rainfall, when humidity shields them from drying. In the process, they redistribute water through their foraging, fragmenting litter into smaller pieces that retain moisture more effectively. This activity creates microhabitats for springtails, mites, and fungi. In effect, the pill millipede is both recycler and engineer, shaping the forest floor's texture and moisture balance. For the human eye, their resemblance to woodlice often obscures their identity. Woodlice are crustaceans, relatives of crabs and shrimps that have adapted to land. Pill millipedes, by contrast, belong to the Myriapoda, sharing ancestry with centipedes and the vast diversity of true millipedes. Despite converging on the same strategy of rolling into a ball, the two groups are distantly related, an example of convergent evolution where similar pressures, predation, desiccation, produce nearly identical solutions. The distinction becomes clear when one counts the legs. Pill millipedes have far more, their many-legged gait unmistakably millipede-like, while woodlice retain the sparser limbs of their aquatic heritage. Reproduction unfolds quietly in the soil. Males court females with subtle antennal strokes, their legs guiding and positioning during mating. Fertilized eggs are deposited in moist soil or leaf litter, where they hatch into small, legless larvae that gradually acquire segments and legs through successive molts. Growth is slow, each molt adding armor and complexity until the juvenile resembles the adult. This incremental development mirrors the patience of their lifestyle, steady, cautious, measured in cycles of growth and decay. Predation events reveal the genius of their defenses. Imagine a night in the forest, the ground alive with hunters. A spider, its eyes glowing under moonlight, pounces on movement, only to find its prey vanish into a sealed ball. The spider probes with fangs, but the armor yields nothing. Chemical irritants sting its palps, and it retreats in frustration. An ant patrol swarms, attempting to bite, but the millipede rolls away like a marble, impervious to their mandibles. The assault breaks off. The pill millipede unrolls minutes later, legs unfurling, and continues its quiet task of grazing on fallen leaves. Victory here is not triumphant but practical. Survival by being more trouble than any predator can afford. Their activity shapes entire ecosystems, yet they often go unnoticed. Because they operate in leaf litter, their presence is subtle, revealed only to those who sift through soil or watch the forest floor with patience. In regions where they are abundant, their contribution to nutrient cycling rivals that of earthworms. Studies have shown that soils enriched by millipede activity have higher microbial activity and faster decomposition rates, highlighting their role as accelerators of forest metabolism. Moisture dependency defines their distribution. Pill millipedes are found in forests across Europe, Asia, and Africa, particularly in areas with rich litter layers and stable humidity. Deforestation, soil compaction, and climate change pose threats by reducing the damp habitats they require. When leaf litter is cleared, their populations collapse, depriving ecosystems of one of their key recyclers. Conservation of these creatures may seem niche, but their absence reverberates through soil fertility and forest health. The night forest is their domain. As darkness settles, the air cools and humidity rises, and pill millipedes become active. They trundle over twigs, push beneath leaves, and gnaw at softened wood. Their armored shells gleam faintly in moonlight, polished by rain and soil. Occasionally, one senses danger and rolls, forming a perfect sphere that rests silently on the ground. Predators investigate, circling, sniffing, tasting the air, and then abandoning the attempt. The ball remains still until the coast is clear. Slowly, plates part, legs stretch, and the millipede resumes its march. In this rhythm of concealment and re-emergence lies the essence of its survival. The pill millipede is no charismatic pollinator, no brightly winged migrant crossing continents. Its drama is subtle, played out in shadows and soil. Yet its importance rivals that of more visible species. By breaking down litter, it fuels the cycle of life in forests. By resisting predation through armor and chemistry, it demonstrates the power of passive defense. And by thriving in damp darkness, it reminds us that ecosystems are not built only by the visible actors above ground, but by the silent recyclers below. To witness a pill millipede roll into a sealed orb and wait out danger is to glimpse a survival strategy millions of years in refinement. It is armor perfected, chemistry deployed without violence, persistence enacted without haste. And when dawn comes and the forest stirs, the pill millipede continues its slow work, filtering air through soil, recycling leaves into life, proving that sometimes the strongest victories are the quietest ones.